In this video, I'm going to be working through the extra Taylor series practice, which is, really it's just a kind of a collection of a few free response problems. It may be called Review 12, depending on, what you're looking at when you're looking at it. Okay, so the first one is 2017 BC number 6. And this one's a pretty good Taylor series question. It's just that it really relies on you getting the first part right and to get the rest of them right, which I think is kind of risky. It's a good problem, and we're going to do it the right way. So it is known that f of 0 is 0, f prime of 0 is 1, and the next derivative is negative n times the previous derivative. Okay, so we'll see how that goes here in a second. What I'm going to do is I'm going to kind of just copy this, and then I'm going to start working to find the value of f double prime of 0, and I'm going to keep going and try to get a bunch of derivatives. So what it looks like is, to get the next derivative, you go to the previous derivative and multiply it by the negative of the order of its derivative. Okay, so that's a little weird. So for the second derivative, what it's saying, for the 1 plus 1 derivative, is to be negative 1 times the first derivative. Okay, so that would be negative 1 times the first derivative, which was 1. F triple prime at 0 is going to be equal to, well, I go back up to, and I probably need that, it's going to be equal to negative 2, right? Second derivative becomes negative 2 times this, which is negative 1, which is 2. F's fourth derivative, move that up now. F's fourth derivative at 0 is going to be negative 3 times the previous derivative was 2, and that's negative 6. And I think if you may or may not be seeing the pattern at this point, but I think after 5 you will see the pattern. That's going to be negative 4 times the previous one, and that's 24. 1, 2, 6, and 24, those are factorial. That's a factorial sequence. So, and we need to be able to recognize that. So maybe I'll come back and I'll write the general nth derivative here, but I was shown a better way of writing the general term of the Maclaurin series for f earlier this morning. So I'll show you that, and then I'll show you how you would actually go through and really show it. So since they already gave us this, right, we can probably figure out the general term. It's what they were saying to me in my third period class, which actually, to me, it makes a lot of sense. So what I'm going to do is I'm going to say, well, the Maclaurin series for f I'm going to get by, well, it's f of 0 plus f prime of 0 times x to the first divided by 1 factorial plus f double prime divided by 2 factorial x to the 2 plus f triple prime divided by 3 factorial x to the 3. Is that all they wanted? Right, the first 4 non-zero terms. That's only 3 non-zero terms. So I'll have plus negative 6 over 4 factorial x to the 4. And if we look at this closely, well, that's minus 1/2 x squared. 2 over 3 factorial. 3 factorial is 3 times 2, so that's going to be a third. Plus 1/3 x to the third. That's what I have here. Minus, and then 6 over 4 factorial. Okay, what is 4 factorial? It's 4 times 3 times 2. Whoops. 4 times 3 times 2. 3 times 2, that's that 6 that we're going to cancel. Okay, so I've got x to the 4 over 4, and I'm happy. The general term, maybe you're just looking at this, and it's like, all right, it's going to be x to the n divided by n with some negativity, right? So it's x to the n divided by n with maybe like a negative 1 to some kind of power. And it seems like it's hold on, it's like, it's negative whenever I've got even powers of x. So I'm going to need this to be like the n plus 1 power there. Okay. And, okay, but how would you show that, without just going off of what they gave you? What we need to recognize here is that the nth derivative at 0 is going to be equal to Well, it seems like I've got this -1 thing going on. It's -1 to the n plus 1 because, again, it's negative when this is even. So I need, -1 to an even number is positive, so I need to add 1, make it odd. And then this is a factorial number, but it's like the previous factorial number. So I'm going to take 5 and I'm going to subtract 1, and then I'm going to do factorial. So it's like subtract 1 and then do factorial. So the general term, remember the general term is the nth derivative at 0 divided by n factorial x to the n, right? Well, that's where I plug in. Whoops, you can't see that. I forgot I had my face on this one. This is where you can plug in, this here. And you can see you get the -1 to the n plus 1. And n minus 1 factorial over n factorial, I can rewrite that as n times n minus 1 factorial. I was just looking for my eraser. And yeah, we'll do that. Okay, and that's, and then that would be where the n minus 1 factorials would come from. And I get -1 to the n plus 1 divided by n x to the n. Okay, how do you want it? Okay, so the second part is going to be saying determine whether this series with 1 plugged in absolutely converges conditionally, or diverges. Okay. Well, let's just go back. I think I'm going to just keep all of this work. I didn't do that very smart way. I guess I'll just bring in a sheet of paper. And I'm going to work over here for part B, right? Yeah. So for part B, I'm going to say that the Maclaurin series for f, I'm going to copy this. It's x plus x squared over 2. Wait, no, that was supposed to be a minus. Plus x to the 3 over 3 minus x to the 4 over 4, and plus so on. And so that's, Maclaurin series for f of x. So for f of 1, I'm just going to replace x with 1, right? I'm going to have 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. You get the pattern. And this is the alternating harmonic series. So what I'm going to say is, what did I say when I worked this earlier? Okay, Maclaurin series, I actually wrote it in summation notation. So this is, I forgot. So the Maclaurin series for f is the sum from n equals 1 to infinity, because there's no constant term, -1 to the n plus 1, x to the n divided by n. I used the general term I wrote in part A. That was maybe smart. F of 1 is given by the sum from n equals 1 to infinity of -1 to the n plus 1 divided by n. Again, this is an alternating series, power 1 on bottom. That means it's going to, okay. So what did I write? Oh, I said this is the alternating harmonic series which converges conditionally. All right. That was part B. Part C is going to ask you to write the first 4 non-zero terms and the general term of the Maclaurin series for g of x equals 0 to x of f of t. Well, no, that's going to be part C. All right, let's move that up right now. So this one we're saying g of x equals the integral from 0 to x of f of t dt. All right, so that means that we're going to anti-differentiate f term by term, right? So it equals the antiderivative. Well, okay, I'm going to probably do something that's not exactly proper, but because we know it's a definite integral, so I'm not going to need a plus c. The c is going to be set by the lower bound, and it is going to be 0. But I'm just going to say, for having f, and maybe I will, kind of just hold on to my work at the beginning of part B. If I had my Maclaurin series for f right there, yeah, it's visible, then that's going to be, well, I know that when I anti-differentiate that, there's going to be a 1/2 x squared and a plus c. So it'll be c plus 1/2 x squared plus 1/6 x to the third. And what do they want first? 4 non-zero terms? Is that what it said? Yeah, and the general term. Okay. That's going to be a 0 term, so I need 2 more. Plus x to the 4 over 12. Maybe I'll write it the way I've been writing it all along. 1/12 x to the 4th. Minus 1/20 x to the 5th. Okay. Because g of 0 is equal to the integral from 0 to 0 of f dt, and that's equal to 0, that indicates to me that c needs to equal 0. Okay. And then I've got, okay, that's the first 4 non-zero terms. And I might just box that off and write an arrow to the reader and say, hey, that's the first 4 non-zero terms. The general term, I'm just going to write over here. The general term above was plus, no, that's going to look bad. But it was x to the n over n with a -1 to the n plus 1. Okay? And I can anti-differentiate that because the only thing that has x in it is this. These are just numbers. Okay, so I'm going to increase the power by 1 and divide by the new power. Or you could see what's going on here. But so it's going to be -1 to the n plus 1, x to the n plus 1, increase the power by 1, divide by the new power. Okay. Or you could look at, it's 4 times 5, 3 times 4, 3 times 2, 2 times 1. That's where those numbers are coming from. All right. That's the general term. That was part C. What is part D? Oh, part D is, I think, pretty nice. So they say that, suppose you're going in and you're going to approximate the value of g of 1/2 using that Maclaurin series. Okay. Fortunately, I've got myself, and maybe I change that to a 0. I've got the first 4 non-zero terms, and they said P4 of x is the 4th degree polynomial. Well, that's going to be 1/2 x squared plus 1/6 x to the 3rd plus 1/12 x to the 4th. And so the maximum possible value of the error in an approximation using P4, so the difference in P4 of 1/2 and g of 1/2, is no more than the absolute value of the first neglected term in the alternating series that represents g of 1/2. So that's going to be that term right here. So it's the absolute value because we don't want this. We can't say the absolute value of something is less than a negative number. That doesn't make sense. So I just take the absolute value of the sum. So -1/20 of x is 1/2 to the 5th. Now, at this point, I need to show you some arithmetic to show you the analysis on why this is less than, what is it, 1 over 500? Yeah. Okay. So what's going to happen is, okay, you could just, if you can't show it, just say that. You just proclaim that it's less than 1 over 500 and move on and hope you're right. That sometimes works. On an arithmetic level, what this is 1 over 20. I'm going to write that as 5 times 2 times 2. And then I'm going to plug in 5 more powers of 2. And you might be like, I don't know how to do that. But you actually do 2, 4, 8, 16, 34, 32, 64, 128. So these 2's make up 128. So in total, this is definitely bigger than 500, which means the fraction is less than 1 over 500. Like that. And on an arithmetic level, that's why it was what it was. Okay. That's 2017 BC number 6. All right, the next one I'm going to do is 2013 BC number 6. And, okay, f has derivatives of all orders at x equals 0. Pn of x is going to be the nth degree Maclaurin polynomial for f. It is known that f of 0 is -4 and p1 of 1/2 is -3. Show that f prime of 0 is 2. Pretty sure I've actually already given you all this problem this year, but you wouldn't recognize it. So, well, what's p1 of x? Just in general. P1 is the first degree Maclaurin polynomial, or the first degree Taylor polynomial for f around x equals 0. So that's equal to f of 0 plus f prime of 0 times x. Divide by 1 factorial, but I'm not going to write that. Okay, so that's pretty nice, right? It's known that f of 0 is -4. And then, so that's P1 of x. And they say when I plug in 1/2, I get -3. Okay, well, f prime of 0 multiplied by x is 1/2. This means that I'm going to add 4 to both sides. 1 is equal to 1/2 of f prime of 0, meaning that f prime of 0 equals 2. And we're happy. That was part A. And I like that. That's a good way to get you started, provided that you knew how to write down the first degree Taylor polynomial. But anyway, B, what am I saying? It is known that f double prime of 0 is -2/3 and f triple prime of 0 is 1/3. Find P3 of x. Oh, I would be happy to do that. And I'll say P3 of x is equal to f of 0 plus f prime of 0x plus second derivative 2 factorial second power triple prime 3 factorial x to the third. And that's P3 of x. Now I need to just go in and replace these with their appropriate numbers. -4, I just found that that's 2. And then f double prime, they said that was -2/3, so -2/3 divided by 2 factorial x squared plus f triple prime is +1/3 divided by 3 factorial x to the third. Now, I worked this problem earlier and made a slight error, and I think it was just carelessness, honestly. But one thing I'm going to do to try to avoid that is I'm going to deal with these fractions right now. Right, this is the third degree Taylor polynomial for f around x equals 0. Now, that was all they asked me for, right? Yeah, find P3 of x. Okay, that's a safe place to stop. What I'm going to do is, in part C, I'm pretty sure I'm going to need that. So I'm going to rewrite P3 of x equals -4 plus 2x. Well, if I take 2/3 and I divide it by 2, I'm going to be dividing the 2 by 2, so I'll have 1/3. And then over here, that's 3 factorial 6 times 3 is 18. And I'm just going to rewrite it like that to avoid the same, tragedy that happened this morning. Couldn't understand why I didn't have the same thing as was on the scoring guidelines. And I just executed the power rule wrong, I guess. Okay, so the function h has first derivative given by h prime of x is f of 2x. It is known that h of 0 equals 7. Find the third degree polynomial for h around x equals 0. All right. So there's a couple of ways of doing this. You should look at the scoring guidelines. Really, like if what I end up doing is very different from what you did, go look at the scoring guidelines. They have 2 ways to do this, and neither of them is what I did. So, just have a look. I'm going to just start by writing down f of 2x and anti-differentiating that term by term, because that's always my first instinct is work with polynomial. They were doing things like taking the derivatives of f of 2x, or there was something else. It was weird, okay? But there are other options for you besides what I'm going to do here. So if P3, which represents f, is this, then f of 2x f of 2x is going to be equal to -4 plus 2 times 2x minus 1/3 of 2x squared plus an 18th of 2x taken to the third power. And again, because I know I made an error on this the last time I worked it, I'm going to say negative 4 plus 4x. When I square that, I'll have 4/3 x squared. And what would that be? 8 over 18 x to the third. Okay. Now I know they want h, so this is, well, f of 2x is h prime of x. Okay, meaning that h of x is just the antiderivative of this thing. And I'm sure there's going to be a plus a dot, 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 right? If we're going to actually say h prime x equal to that. So h of x is going to be an antiderivative, so there's going to be a plus c. There's going to be a negative 4x plus 2x squared minus 4/9 x to the third. You know, when I increase the power by 1 and divide by the new power, that was what I had trouble with. I had 4x to the third because I made an arithmetic error. And that's how it goes. Well, they only actually wanted the third degree polynomial, right, for h? Yeah. So this is good. I'm going to just put plus dot, 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 right? I don't even need to do this because they don't care about it. So I need to figure out what the c is. H of 0 is equal to 7, which is going to be equal to c minus 0 plus 0 minus 0 plus, a whole bunch more zeros, so 7 has to equal c. So the third degree polynomial for h of x is going to be 7 minus 4x plus 2x squared minus 4/9 x to the third. Whoops, there it is. Okay, and that's the, well, I lost the problem, but 2013, BC6. Let's get another one. Got two more. All right, this next one comes with a graph, and that means that they're probably going to ask you about the Lagrange error bound. Okay, and yeah, especially because they're showing you the graph of the absolute value of a high-order derivative. Gotta be a Lagrange error bound situation. I will bring that graph back up when I need it, but that's not going to be until part D. So I'm just gonna, give myself some room here. All right, let f of x be sine of x squared plus cosine of x. So you know they're going to be asking about those Maclaurin series you're supposed to know. Right, write the first four non-zero terms of the Taylor series for sine x around x equals 0. I can do that. Sine x's terms it's the odd function. It's got odd terms in its Taylor series. So I'm going to say I'll have x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. First four terms of sine of x, right? First four non-zero terms of the Taylor series for sine of x squared. Okay, in a free response setting, I'm going to tell you, just replace it with x squared. Okay, happy. Okay, that's sine of x squared. That is 3 points out of 9 on this one. 1 point for this one, 2 points for that one. I thought that was pretty generous. All right, write the first four non-zero terms of the Taylor polynomial for cosine x around x equals 0. And, okay, I'm going to have to do that. All right, use this series and the series in part A to write the first four non-zero terms of the Taylor series for f around x equals 0. We can do this for sure. So for part B, cosine of x is going to be, it's the even terms, 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. Okay. Meaning that f of x, which is the sum of these two things, sine of x squared plus cosine x, well, I'm just going to kind of add it term by term. So I have 1, I have no regular x's. I'll have 1x squared minus half of x squared is plus 1/2 x squared. Let's see, am I going to have any x to the third terms? I'm not. Okay, I will have x to the fourth terms, though. It'll be right here. Plus 1 over 4 factorial x to the 4. That's 3 non-zero terms. I just need one more. I don't see any fifth power terms. I see a sixth power term and a sixth power term. And then, oh, okay, yeah, I'll be honest, I'm not going to be doing this arithmetic, right? Because I'll have minus 1 over 6 factorial x to the 6th minus 1 over 3 factorial x to the 6th. So maybe I'll just put the minus here. Okay, so that's the first four non-zero terms for f of x. Okay, I don't know. Maybe there's some kind of arithmetic I'm missing here. I don't even know what 6 is. That 720?
Yeah.
And that's 6. So I mean, there's a common denominator situation in there somewhere, but like, who cares? That's 4 non-zero terms for f of x, right? We're happy. I'm not sure. Yes. Yes, absolutely. Yes. This is. I mean, I'll look on the scoring guidelines maybe, but I can't imagine, because the only thing I know to do with this is give these both a denominator of 720. I had to ask for verification from students in my class that 6 factorial even was 720, so I wouldn't be taking that risk myself. Because if I was sitting taking the AP exam, I would not have y'all to consult with about arithmetic, right? It's true. All right, so that was part B. Part C, I love this part. Find the value of f's sixth derivative at x equals 0. This is great. We know that the value of f's sixth derivative at x equals 0 divided by 6 factorial x to the 6th is the x to the 6th term I'm seeing in the Taylor polynomial. So that's negative of 1 over 6 factorial plus 1 over 3 factorial x to the 6th. So we can solve for this thing. We're going to start by, dividing both sides by x to the 6th. Multiplying both sides by 6 factorial. And I'll say f's sixth derivative at x equals 0 is the negative of 6 factorial multiplied by 1 over 6 factorial plus 1 over 3 factorial. Okay. There is a multitude of ways you can write this. I would say the most common other way to write this would be the negative of 1 plus 6 factorial over 3 factorial. And that's 120, I think. 6 times 5 times 4, yeah, it is. But you don't need to say that's negative 121. Like, you definitely don't need to. What they had done... Oh, that's interesting. Was they had, I remember in the scoring guidelines, they'd combined this to say it was 121 divided by, I guess, 6 factorial. Yeah, that was what they said. So they did the arithmetic, and that made this part a little easier, but I just don't, it's not worth it, right? Because if we mess this up, not only are we wrong here, but we're probably wrong here also. I don't know if they would allow an imported wrong answer for this question. I have no idea. I was not even teaching Cal BC in 2011. So let P4 be the fourth degree Taylor polynomial for f around x equals 0. I think I can show you P4. That would be just this, or, just that, okay? Use the information from the graph of y equals the absolute value of f's fifth derivative shown above to show that the error in an approximation of f of 1/4 using a fourth degree Taylor polynomial is less than 1 over 3,000. Okay, this is another one of those ones where it's there in the arithmetic. Okay, I just need to, I'm going to show that there so I can come back to it. But for part D, just to remind you of how the Lagrange error bound works, because it's been a second, is its error is no more than, we're going to maximize the next derivative. Okay, but the thing about this is that there's always an implicit like approximation going on with this Lagrange error. So the Taylor centered at x equals c, and we are approximating f of some particular x value using an nth degree Taylor polynomial. So that's why we use the n plus first derivative, the maximum possible value. And I mean, I'm going to assume with no loss of generality that x0 is greater than the centering point. So I'm going to say for c is less than or equal to x is less than or equal to x, the approximation point. If the approximation point was before the centering point, like to the left of the centering point, it would just be the opposite. It would be x naught less than or equal to x, less than or equal to c. Okay, we take that, we divide by n plus 1 factorial, because it's the next derivative, not n plus factorial, that doesn't even make sense. Next derivative, next factorial, next power. I guess it's x minus c to the n plus 1. But since we're centered at 0, all of that's going to become 0, right? So our one that they're talking about is they're going to use a 4th degree polynomial to approximate f of 1/4. So to use the same language I was using before, c equals 0. So maybe I'll use some color here. Because it's centered at 0. We are using a 4th degree polynomial to approximate f of, what was it, 1/4? Yeah. All right. So I'm going to say I've got, just barely enough room. Okay, looks a little weird and paper's bunching up. But I'm going to say the maximum possible difference in, what was it, P4? Yeah, P4 of 1/4 minus g of 1/4. It's going to copy this. The maximum possible value of f's 5th derivative, because it's the next derivative, on the closed interval 0 to 1/4. This is what we're going to get off of the graph. We're going to divide by 5 factorial, and we're going to multiply by, whoops, pardon me, that was supposed to be an x naught up there. Because this always works the same. We always put in the biggest, the approximation value, because that makes this thing biggest. So 1/4 minus 0 to the 5th power. What am I even going to do with this? First of all, we need to figure out what this maximum value of s 5th derivative is on 0 to 1/4. Well, that's 1/4. And like I told you when we were first learning about Lagrange error bound, like the number that you're supposed to use, almost always, not always, but like if they give you a graph, this is for sure the case. The number you're supposed to use is printed on the piece of paper. So I'm going to use 40. Okay. Which is a little bit of a generous, maximum, but I'll still be able to show that this is less than 1/3000 or whatever they want. Yeah, 1/3000, without too much difficulty here. Whoops, there we are. Okay, so this is less than or equal to, I said that was 40 divided by 5 factorial. Well, 5 factorial is 5 times 4 times 3 times 2. And then I've got 5 powers of 1/4. So what I need to do is I need to take this 8 and this 5 and cancel them with the 40. That's going to be the first trick. And then I'm going to have, well, I've got a 3. That's probably going to help with 1,000. And I've got 4 times 4 times 4 times 4. And maybe you don't entirely see this, so I'm just going to call it 3 times, well, 4 is 2 2s. It's 8 powers of 2, right? 2, 4, 6, 8, yeah. 2, 4, 8, 16, 32, 64, 128. I'm missing an entire...
I have a question. Is there another 4
There should be. Whereas, oh yeah, because it's 5 powers of 4. I was like, I need another 4. Thank you up there. I don't know your number yet, but I will know it. I'll know it in August, and I'll refer to you by it in the future. I don't want to say your name out loud in case you'd be embarrassed. I don't think you would, but, you know, better safe than sorry. So that's going to be an extra couple of 2s. I was like, yeah, I didn't go how I was supposed to. That was not going to be less than 1 over 3,000, right? That's troublesome. Right, I need to have 5 powers of this 4, and yet I only had 1. I only had 4. Yeah, this is my new one. Whoops, thank you. All right, so let's count again. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024 times 3. There it is, right? They don't expect you to do like the most arithmetic ever, but I wish they had like a list of the things that you're actually supposed to know arithmetic-wise. But powers of 2 does seem to be in there. This is bigger than 3,000, so this fraction is less than 1 over 3,000. Okay, that was a lot of discussion on an arithmetic level. Again, if you can't figure out how to show it, you're going to start here, and you're just going to proclaim that's less than 1 over 3,000, and I will forgive you for proclaiming the answer. We do what we must when it comes to the AP exam, right? Now, the last one I've got for you is 2015 BC number 6. Okay, you can't see it, but it's up there, 2015. And this one's pretty interesting. We're going to use the ratio test to find the radius of convergence of the Maclaurin series. This is pretty straightforward. All right, this is... I'm going to do the ratio test. I'm going to be considering the limit as n approaches infinity of the ratio of an plus 1 to an absolute value. And I'm going to eventually be interested in where this is less than 1. Oh, wait, no, I just want the radius, so this will take less time. So this will be the limit as n approaches infinity. If when I plug in n plus 1 for n in the general term, I'll have negative 3 to the n minus 1 plus 1. X to the n plus 1 divided by n plus 1 multiplied by the reciprocal of what I'm seeing here. So I'm going to see an n in the numerator. I'm going to see an x to the n down here and a negative 3 to the n minus 1. All right. Pardon me. All right, so I'm going to be canceling off some factors of negative 3, right? I have n minus 1 and n up here, so I'll just be left with 1 up top. Over here, I'll also be left with 1 power of x in the numerator. And then I'll have the n over n plus 1, which as n goes to infinity is going to get closer and closer to 1. So it'll be the limit as n approaches infinity of the absolute value of negative 3x multiplied by n over n plus 1, which is going to be the absolute value of negative 3x, which is going to be the absolute value of 3x. Same thing. All right, so I'm going to just say that's 3x. Okay, and I'm interested in where that's less than 1. So I would have to divide by 3, right? Or you could say this is x divided by 1/3 if that's how you know to look for the radius of convergence, is you know it's the number that we divide x by. We end up multiplying. So basically, that radius equals 1/3. Or you could just say that's going to be 3x is negative 1 to 1, negative 1/3 to 1/3. If you were unsure about the radius therein, you could draw 0, you could draw 1/3. You could draw yourself like a circle. This isn't going to actually be a circle, but I could say the radius is 1/3. I don't know what else to say. All right. In part B, they're going to say, write the first 4 non-zero terms of the Maclaurin series for f prime of x. Well, I'm going to take that term by term. I'm going to actually, since I don't think I need that anymore. Express f prime as a rational function for x being within the radius of convergence. Okay, that's going to be a little tough. I don't think I've asked you to do one of those yet this year. But who knows? Maybe you'll just see what we're supposed to do here. So for part B, I'm going to just take the derivative of this term by term. I need the first 4 non-zero terms. All right. 1 minus 3x plus 9x squared. What would the next term be? Okay, well, I take the derivative, and it's going to be n over n, and x to the n minus 1. So it's just negative 3 to the n minus 1 times x to the n minus 1. So what's going to happen here? I got started at n equals 1, n equals 2, n equals 3. I need to plug in n equals 4. That's just frustrating. Hold on. What is the next term going to be here? It's going to be negative. When I plug in 4, I'll have negative 3 to the third. Oh, interesting. I guess I'm going to have minus 27 over 4x to the 4. Yeah, that's what I want. Okay, that's what would go here. And when I take the derivative of it, I'll have negative 27x to the third. I don't know. Cover that up. That's the first 4 non-zero terms of the Maclaurin polynomial, Maclaurin series for f prime. Express f prime as a rational function. What does that even mean? We got to write it as a fraction. How could I add all of these things up? It's like, oh, look at the pattern. It's a geometric series. And we have a formula for the total of a geometric series. What we're going to do is we're going to go over here. We're going to say f prime of x is equal to the first term times 1 over 1 minus the common ratio. What am I multiplying by each time? Negative 3. Okay, I don't know if I would function. Wait, not negative 3, minus 3x. Right? Yeah. So what I'm going to do, I might just rewrite this as 1 over 1 plus 3x. That looks more like a rational function to me. Okay, that's how we did part B. Took the derivative term by term, realized it was geometric. All right, write the first 4 non-zero terms of the Maclaurin series for e to the x. Use the Maclaurin series for e to the x. Write the third degree Taylor polynomial for the function that you get when you multiply f of x and e to the x. That's interesting. We can do that. I'm just going to find myself a fresh sheet of paper, I think. Because when I first worked this problem earlier today, I made the mistake of trying to distribute e to the x times f prime of x. And it got much worse, right? We don't want that. So what we're going to do is we're going to say, well, I can start with e to the x. That's what they wanted. First 4 non-zero terms. 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial. Great. Polynomial for g of x equals e to the x f of x. Well, f of x, I've got the terms of the polynomial up here. That's going to be x minus 3 halves x squared and positive 3x to the third. And you see I'm setting up for some box distribution. I have x minus 3 halves x squared and plus 3x to the third. Here I'll have an x squared, a negative 3 halves x to the third, and something with a power that is bigger than 3, which means I don't care about it. Over here, this will be the last one. This will be 1 half x to the third, because this one, well, I don't actually need to multiply it by anything because I've got that x there, and I would have too much power, right? So what I'm going to do is I'm going to write they're asking for the third degree Taylor polynomial for g. So g of x, its third degree Taylor polynomial is going to be x. If I have 1 x squared and I lose 1.5, I'll have negative half. And then this one, okay, wait a second. If I have 3 and I lose 1.5, I'll only have 1.5 left. And I add 1/2 back, I'll have 2. plus 2x to the third. And that's the third degree Taylor polynomial for g, which is e to the x multiplied by f of x. I had to throw that one in there that had that kind of, infinite distribution, because those are the ones that always seem difficult, but they're not so bad once we jump into them, because kind of the scope of them is limited. We only care up to the third power. Okay. And I think that's it, right? That's all the problems. Yeah, okay, cool. All right, well, thanks for watching. Hope it was helpful.